Okay, November 2022, paper 6, variant 1. Yeah. Question 1. Explain briefly how to measure the center of the pendulum bob as accurately as possible. How can I measure to the center of this pendulum? Using the ruler, definitely. Using a ruler. So all you need to do is um, you can draw if you want to. You can draw the ruler, okay, vertically, which has to be very close. Okay, it needs to be kind of touching the bulb or whatever. Explain briefly how to measure. Okay, using a ruler. Okay, using a ruler, which is very close to the pendulum. You can say take the reading perpendicularly to avoid the parallax error as well, if you'd like. Calculate and record in table 1.1 the period of the pendulum. The period of the pendulum. He measures and records the time for 20 oscillations. Can I find the period for one pendulum for one cycle? Yes, definitely I can find the period for one cycle, just divided by 20. So 28.2 divided by 20. 28.2 divided by 20 is around 1.1, 1.41. 1.41. So this is the period of one cycle. Can I find t squared? Yes, 1.41 squared. 1.41 squared. Using the calculator, it would be around 1.99. 1.99. So this is t squared. He repeats the procedure for values 60 and 70, 80 and 90, and he has some readings. Then I'm required to draw the graph. First of all, plot t squared slash s squared on the y-axis. T squared slash s squared on the y-axis, and L slash centimeters on the x-axis. L slash centimeters on the x-axis. Start the t squared at a convenient value. Close to the minimum value of t squared slash s squared. Close to the minimum value of t squared. So you're not required to start from the origin. Not required to start from the origin. T squared starts from 1.99 all the way up to 3.67. So no, you cannot start from 2. Definitely, you cannot start from 2. We can start from probably 1.8, maybe 1.5. Let's see. We need to go all the way up to 3.70, 3.65. You need to go all the way up to 3.65. So can I start from 1.5? Let's see if I can if I can start from 1.5 or not. If I say 1.5 and then 2, 2.5, 3 and 3.5, I guess this would be suitable. It would be suitable. Why? Because I'm starting all the way from 2 up to 3.65, which is around here. So we took more than 50% of the graph, which is okay. Which is okay. Okay, so this is quite sufficient. 3.5, and you can go all the way up to 4.0. What about the length? The length starts from 50, 60, 70, 80, 90, so we can just plot them. Okay, 50, 60, 70, 80, and 90. If you want to start from 40, go all the way up to 90. Okay, if you want to start from 50 and go all the way up to 100, it would be okay. Okay. Moving on to the next question, determine the gradient. Oh, we haven't we haven't plotted the numbers yet. Yeah, let's plot the numbers. 1.99 and 50, or 50 and 1.99, which is basically 2. Okay, basically it is 2. And then the second point would be 60 and 2.43. 60 and 2.43. So this is hmm, each small square, or each two squares, each two small squares are zero point 0.1. Point 1. So 2.43 is just below 2.5, which is around 2.45. Um, I'm sorry, this is with 60, not with 70. With 60, so it's here. 70 and 70 and 2.82, 70 and 2.82. So this is 2.9, 2.82 is here. Okay, this is 2.82. 80 and 3.2, 80 and 3.2, 3.1, 3.2. And last but not least, 90 with 3.65, 90 and 3.65, 3.56, and 65. This is 65. Okay, 3.65. Can I draw the line of best fit? Definitely, I can draw the line of best fit. Using, let's use a different color, blue. Okay, straight line. This would be an okay line of best fit. We have 1 point below, 1 point above the line. This is definitely a good line of best fit. For the next question, he is asking, can I find the gradient? Yes, I can find the gradient. Show clearly on the graph. How can I show clearly on the graph? By drawing two straight lines, okay? Triangle method, rise over run. We need to join two very distant points. You need to join two very distant points on the graph. When you join these 2 points on this graph, you have a triangle, a rise over run. Can I find the rise over run? Yes, I can find it. You can calculate it y2 minus y1 over x2 minus x1. But again, you have to. You must show on the graph. You must draw this line. You must draw the line. y2 minus y1, you can say 3.65 minus 1.99 over 90 minus 50. Okay, let's calculate it. This would be 0.65 minus 1.99 over 40, which is 0.0415. 0.415. Okay, I can just remove the line now. Hmm. Okay, I have no idea why isn't this line being removed now. But I'll okay. Let's try to remove the line again. It doesn't want to get removed. Okay, 1 second. Okay. Explain briefly why timing 20 oscillations gives more accurate results for the time period than timing one oscillation. Why is 20 much better? Why is 20 much better? I've always said you need to increase the number of oscillations. Why? Because there is a human error. There is a human error. So when you increase the number of oscillations, what happens to the percentage of the human error? The percentage of the human error decreases as you increase the number of oscillations. Okay? Percentage of human error decreases. Percentage of the human error decreases. Hmm. Okay? The human error, as it's the human error is always around zero point 0.5 seconds, so it's almost always constant. So you can't decrease the actual human error, but you can decrease the percentage of this human error by kind of diluting it when you increase the number of oscillations. Um, okay. Question two on figure 2.1, draw a voltmeter connected to measure the potential difference across the lamp. Okay, the voltmeter would measure the potential difference across this lamp, above or below the lamp. She measures the voltage and the current, and then she calculates the resistance. The voltage in this question would be 2.4. The voltage would be 2.4. 2.4. 2.40 if you'd like. And the current would be 0.32. This is 0.32, yes. Can I find the resistance? Yes. 2.4 divided by 0.32, which would give you a resistance of 7.5. And the unit is ohms. 7.5 ohms. She places the sliding contact S on the resistance wire as close as possible to point D, as close as possible to point D. She measures the potential difference V2. So V1 was 2.4, V2 was 1.4, I2 was 0.24. Can I find R2? Yes. 2.4 divided 1.4 divided by 0. 1.4 divided by 0.24, which gives you a resistance of 5.8 or 5.83 if you'd like. 5.8, again, the unit is ohms. V3 was 0.9, I3 was 0.18. Can I find R3? Yes, R3 would be 0.9 divided by 0.18, which is 5 ohms. 5.0 to be more accurate. Okay, 5.0 ohms. Complete the following statements. Can I complete the following statements? I guess so. Complete as the length of the resistance wire included in the circuit increases, the brightness of the lamp. The brightness of the lamp as the length increases. What happens to the brightness of the lamp? I know a lot of you would be tempted to say as the length increases, the brightness should increase. But if you check out the circuit, as the length increases, as the length of this wire increases, the resistance of this wire increases. We can write it down. As the length of this wire increases, what happens to the resistance of this wire? It increases. Therefore, the potential difference or the voltage of this wire increases. So when the voltage or the potential difference of this wire increases, what happens to the potential difference of the lamp? It decreases. Potential difference of the lamp decreases, and therefore the brightness of the lamp also decreases. Brightness is directly proportional to the voltage or the potential difference. So he's asking what happens when the length of the wire increases. Therefore, the brightness of this lamp would definitely decrease as the length of the wire included increases. What happens to the resistance of the lamp? The resistance as well decreases. So you can say the resistance decreases, the voltage, the potential difference decreases, the brightness decreases. They are all directly proportional. A variable resistor, okay, can be used in this type of experiment. Draw the circuit diagram to show a variable resistor. Okay, include the ammeter and voltmeter in the. Can I draw the whole diagram again? But instead of drawing this length, this sliding contact, can I draw the variable resistor? Yes, include the ammeter and the voltmeter. So I'll just copy this diagram. You just need to copy the diagram. Now we have the power, and then this was the lamp, okay, and then you have the variable resistor with the ammeter, okay, and the voltmeter on this side. I hope I haven't forgotten anything. A switch, okay, let's draw the switch. And this is the switch. That's it. A very simple diagram, 3 very easy marks. 3 extremely easy marks. A student investigates the effect of starting temperature on the cooling rate of water. Okay. Can I find the theta R, the room temperature? Can I find the room temperature? Yes, the room temperature is around 23 degrees Celsius. Do not forget the unit. 20, the unit is already written. 23 degrees Celsius. The student uses a measuring cylinder to pour 200 centimeters cubed in the water. The temperature of the hot water at time 0 was 88. He measures the water temperature every 30 seconds. Can I complete the time column? Definitely I can complete the time column. I just need to increment by 30. So 0, 30, 60, 90, 120, 150, and 180. He just needs to make sure that you have passed year 5. Okay? He just needs to make sure that you know how to count. Calculate the decrease in temperature delta theta 1 between 0 and 180. Between 0, which was 88, and 180. So 88 minus minus 67. 88 minus 67, which is 21 degrees Celsius. 21 degrees Celsius. Can I find C1? Can I find the average rate of cooling C1? Yes, delta theta 1 over delta T, where delta T is 180. So basically 21 over 180, and I will include the unit. 21 over 180 is around 0.17, 0.117. 0.117. Can I write it down as 0.12? Yes, you can. Okay, two significant figures. The unit is degrees Celsius per second. Temperature over time. Degrees Celsius per second. Okay. The student empties the beaker. He pours warm water into the same beaker. He records the temperature as well. Use table 3.2 to calculate the decrease in temperature between 0 and 90. So it started at 74. It reached 68. So 74 minus 68 is... Okay, 74 minus 68 is 6 degrees Celsius. Can I find C2? Yes, 6 over 90. 6 over 90. Okay, 6 over 90 is 0.06, I guess, 0.0666. So we can just write it down as 0.067 degrees Celsius per second. Degrees Celsius per second. A student suggests that the rate of cooling of water depends on the initial temperature of the water. Write a conclusion about the effect of the initial temperature of the water on the rate of cooling. Based on the results, justify your conclusion by reference to the values. Justify your answers. Does it actually depend on it? Yes, definitely it depends on the initial temperature. Why? Because as the initial temperature decreases, what happens to the rate of cooling? In the first example, the initial temperature was 88 and the rate of cooling was 0.12. 0.120, or it was actually what it was 0.117. It was 0.117. For the second experiment, the initial temperature was 74 and the rate of cooling was 0.067. So this is 67, this is 117. Definitely there's a huge difference. There is a significant difference. So the conclusion, as the temperature or as, let's say, the initial temperature of the water, let's be very specific while writing down, as the initial temperature of water decreases, what happens to the rate of cooling? The rate of cooling decreases as well. Justification. Okay, delta theta 1, or let's say theta 1, okay, was 88. Theta 1 was 88, and C1 was 0.12 degrees Celsius per second. Theta 2 was 74. It was 74, wasn't it? Yes. And C2 was 0.067 degrees Celsius per second. State two requirements when reading the volume of water in a measuring cylinder in order to obtain an accurate result. Two requirements to obtain accurate results. Two very, very important precautions while dealing with any measuring cylinder. Two very important precautions, which are, first of all, you need to take the reading perpendicularly. Take the perpendicular reading. Take the reading perpendicularly. Why? To avoid the parallax error. Parallax error. Okay. And second of all, you need to take the reading from the bottom of the meniscus. Take the reading from the bottom of the meniscus. Suggest two possible variables that the student should keep constant. Two possible values. Definitely, we have many variables. Actually, we have many variables. One of them would be the volume of the water. Okay. Another one would be the room temperature. The time taken. Okay. The time taken. These are three very important variables. Stating or actually saying one of these variables, um, if you want to say that one of these variables would be the initial temperature, it would be wrong. Why? Because this experiment, what am I doing in this experiment? I'm trying to find if the initial temperature actually affects the rate of cooling or not. Okay, so stating that the initial temperature would be constant, this would be wrong. This would be wrong. So two possible variables would be the volume, okay, of the volume of the water, and let's say the initial, okay, not the initial, I mean the room temperature, the room temperature. I know that most of us are used to saying initial temperature of water. Material of the container. Material of the container. It wouldn't be wrong. It wouldn't be wrong. Okay. You could say it. But these are more accurate. It's not wrong saying the material of the container is not wrong. But these are more accurate. The volume, the water, and room temperature. Okay. The time taken for this whole experiment. Like for example, in the first experiment, he took 180 seconds. In the second experiment, he took only 90 seconds. So this is wrong. This is wrong. Hmm. Okay. Question 4. A student investigates the horizontal distance traveled by a metal ball after it rolls off the end of a plastic track. The ball rolls down the plastic track. Okay. Plan an experiment to investigate how the horizontal distance, okay, traveled by the ball depends on the angle that the right hand end of the track makes with the bench. It's not that difficult if you think about it. You need to find what? Okay, you need to see if the distance traveled by the ball. You have the ball. Okay, I'm leaving the ball. It will travel down the track and then up this angle, and it will travel in the air and fall somewhere. Okay, on the floor. We need to measure this distance. We need to measure this distance d. You need to measure this distance. Is this distance affected by this angle? He said this angle. Which angle? On the right hand end of the track. You need to find this angle. Okay. You need to change actually this angle and measure it. When I change the angle, I will measure it and see whether it would affect the distance traveled by the ball or not. Okay, so this is the whole experiment. I'll keep on changing the angle. As I change the angle, I will see whether it would affect the distance or not. Question is, what is the range of values? What is the independent variable that I will be changing? First of all, to just write it down, what is the independent variable? The range of values is the angle. So basically, you should write down the range of values. What is the independent variable that you're changing? The independent variable is the angle of the right hand end. Right hand end. Can I write down some values for this angle? Yes, definitely. We can say what? 15 degrees, 20 degrees, 25, 30, and 35 degrees. Okay, definitely do not go up to 90 degrees. If the angle is 90 degrees, the ball would instantly stop. It wouldn't even go up the slope. I need an apparatus for this. I need a protractor. Okay, I need a protractor. So list any additional apparatuses. I will use a protractor. Explain briefly, state the key variables, draw a table, and show how you'd use how you would you reach the conclusion. Okay, we need two main things. We need two main apparatuses for this question. We need the protractor and you need a ruler. That's it. You need a protractor and you need a ruler. Why? Because you need to measure this distance and you need to measure the angle. What are some of the constants, controlled variables, the controlled variables that we have? Controlled variables. If you think about it, okay, if you think about it, one of the main controlled variables, one of the most important controlled variables in this question is the position at which the ball is released from. You're not pushing the ball, so I don't want anyone to say the force or the initial speed of the ball. The initial speed of the ball is zero. Okay, there's no force. You're not pushing the ball. You're just releasing the ball from an initial position. So one of the constants is the position from which this ball is released. Controlled variables. Okay, the position from which the ball is released. Okay, what else? The position from which the ball is released. The same ball. You actually need to use the same ball, the same mass, same material, same. It's the same ball. Do not change the ball. The same mass of the ball, same material. If you want to go on saying same material of this curve or whatever, okay, so I have several things, okay. Um, okay, so these are some of the controlled variables. What about the apparatuses needed? Okay, some of the apparatuses would definitely be the meter ruler, and the protractor. Meter ruler and the protractor. Now, can I state the steps? Can I write down the steps? Yes, I can write down the steps. What should I do? Release the ball from a fixed position. Leave the ball until it hits the ground. Measure the distance. Okay, measure the distance traveled or the horizontal distance traveled on the floor. Okay. Steps. Release the ball from a fixed position. Measure the distance or the horizontal distance traveled to the point of impact, to the point of impact, okay, on the floor, okay, measure the distance traveled to the point of impact on the floor. And then you can repeat and take average, okay, repeat for each ball. That's it. That's it. Yes. يعني there's no, you don't have too many details to talk about. Okay, you don't have too many details to talk about. Um, mm, can I draw the table? Yes, I can draw the table. You have only one one variable that you're changing. What's the one variable? The angle, and the dependent variable would be the distance traveled. So we have the angle in degrees, and then you have the distance in centimeters. You're changing the angle, and therefore you want to measure the distance traveled in centimeters. And then can I write down a conclusion? A very simple conclusion. Yes. For each angle, because you're changing the angle. For each angle, what should I do? For each angle. Repeat the experiment. Repeat the experiment and take average. And take average. طب after I repeat the experiment, take average. What should I do? Record the results in the table. يلا record the results in the table. And then last but not least, compare your results. Compare the results using a graph. You can draw a graph if you want to. Okay, compare the results using a graph to see whether the angle affects the distance or not. Okay, using graph to compare, yeah, to compare the distance traveled with the angle. With the angle. That's it. That's it for this exam.